Introduction to Robotics, Inverse Kinematics. Inverse kinematics is a procedure in robotics in which the joint variables are calculated or computed in order to achieve a certain desired end effector position or orientation. So in this example, we have a planar 2 degrees of freedom RR standing for revolute to revolute, as shown here by theta 1 and theta 2, two revolute joints, as shown in the figure, and we are required to find the values of these two angles that are required to accomplish a certain desired position of the end effector. And when we say x and y, in reality what we really mean is x3, which is the x position of the origin of frame 3 with respect to the base frame, 0 frame, and the same thing for the y, which is the y coordinate of the origin of frame 3 with respect to the base frame. A couple of lectures before, we already talked about the homogeneous transform matrix, and we said that this matrix is very important as it describes the position and the orientation of one frame to another. So since there is a desired position and sometimes also a desired orientation for the end effector with respect to the base frame, that means that the corresponding matrix, homogeneous transformation matrix, T3 to 0, 3 here for this example represents the end effector with respect to the base. So this matrix should be given. So we have a desired value for x for the end effector, a desired value for y of the end effector, and also in many cases also we could have a desired orientation phi, an angle phi. However, honestly speaking, for this example, we only worry about the position of the end effector, and we don't care a lot about the orientation at which it will be pointing at. We talked about forward kinematics in a previous lecture where we obtained the transformation matrices for frames 1, 2, 3 for this particular example, and we saw that T1 with respect to 0 represents the transformation matrix for frame 1 with respect to frame 0, where we have the orientation of the frame and we have the position of its origin with respect to the origin of frame 0. And we did the same thing for the T2 to 1 and T3 to 2. And just as a reminder, you can see that this part here, we can see that this part here corresponds to the orientation. This is the rotation matrix of frame 1 with respect to frame 1 with respect to frame 0, and this is the it's a rotation about the z-axis by an angle of theta 1. This is why we have cosine theta 1 minus sine theta 1 0 and so on. This is like one of the basic rotation matrices. And this here, these three numbers, these correspond to the position of frame 1, origin of frame 1 with respect to frame 0, and we can see that both frames have the same origin. This is why this is going to be zeros. These going to be zeros. Then we have for transformation matrix for frame 2 with respect to frame 1. You can see that when you compare frame 2 to frame 1, you can see that frame 2 is rotated about the z-axis by an angle of theta 2. And this is why we have here the basic rotation matrix about the z-axis, but this time by an angle of theta 2. And when it comes to the position of frame 2 with respect to frame 1, So it is translated about the x-axis by L1. So you can see that this distance, this is L1. So, and it's along the x1 axis. So this is why we have L1. The rest are going to be zeros. And finally, for frame 3 with respect to frame 2, there will always be parallel. This is why the orientation matrix is the identity matrix, and the position of frame 3 with respect to frame 2 is translated along the x2 by an amount of L2. Also, part of the forward kinematics would be finding the transformation matrix for the end effector frame with respect to the base frame. And this can be obtained by multiplying the transformation matrices that we found in the previous slide for each frame with respect to the one before it. And thus we have to multiply these three matrices. We start by taking the first two, and you can see that you can take row by column as usual. So you can see cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus 0 will give me this term here. And we do the same for the rest of the elements in this matrix. And before proceeding, we need to really realize that this corresponds to this trigonometric identity, where we have the cosine of an angle times cosine of another angle minus sine of the first times sine of the second is going to be equal to cosine the summation of these two angles. So this is why we can replace this term with cosine 1, 2, where cosine 1, 2 is cosine of theta 1 plus theta 2. And we do the same for the rest of the elements of this matrix. Then we take, we have to multiply these two matrices to get the final result for the transformation of matrix of frame 3 with respect to the base frame. So conducting the multiplication by the two matrices will give me finally the result of the forward kinematics, which is the transformation matrix of frame 3 with respect to frame 0. So what we have here is if we know the values of theta 1 and theta 2, we can find out the orientation of frame 3 with respect to the base frame, and we can also decide on the position of its origin with respect to the base frame. So up to this point, really what we were solving for is the forward kinematics, if you had the chance to look at the previous lectures. However, starting from now, we're gonna go and work with the inverse kinematics. So in inverse kinematics, we're gonna try to find the opposite. If we have the position, for this case, if we have the position of the end effector, what would be the corresponding values for theta 1 and theta 2? And to do this, we need to compare the result that we obtained here with the general transformation matrix for the end effector with respect to the base frame. So this general transformation matrix will, of course, consist of the rotation matrix and a position for the end effector. Now we try to populate this matrix with known values or desired values. So for the orientation, in this case, is going to be straightforward. It's a rotation about the z-axis. So if you compare frame 3 with respect to frame 0 here, we can see that we only have a rotation about the z-axis. So this is why we have the basic rotation matrix about the z-axis by an angle of phi. So phi is from the x0 towards the x3. And we also see that since it's planar, it's a planar robotic arm, the z will always gonna be 0, so we're going to have an x and a y. So in inverse kinematics, not all problems it will not be easy for all problems to really determine the orientation. And if we couldn't really determine it, we can just keep it as like R11, R12, representing any given certain orientation. And as I said before, for this problem, the focus is mainly on the position of the end effector. So we have x, y, and zeros, and a 0. Now, so the inverse kinematics problem would start with comparing the result here of this matrix with the one here. So we can see that the cosine phi should be equal to cosine theta 1 plus theta 2, because both of them correspond to the same matrix. Same thing here, sine phi should be equal to sine theta 1 plus theta 2. We have the x should be equal to cosine theta 1 plus theta 2 times L2 plus cosine theta 1 times L1, as we have it here. And y should be equal to sine theta 1 plus theta 2 times L2 plus sine theta 1 times L1, and we have it here. So in this orange box, I have the result of the comparison between these two matrices. I'm going to take this result to the next slide, and we'll see how we're going to proceed in order to extract values for theta 1 and theta 2. So here, again, these are the equations, and mainly we're interested in equation 3 and equation 4, as I mentioned before. Now, how to solve these equations? It's honestly speaking, it's not that straightforward. You may need to do some to give it some thought, to do a little bit of trial and error, but usually in many cases it turns out to be useful to follow something similar to this, where we take one equation, square it, and add it to the square of the other equation. So this is what I'm going to do here. I'm going to take equation 3, square it, and add it to the square of equation 4. So we'll take x squared plus y squared on the left side of the equation. On the right side of the equation, I'm going to square this term here and add it to the square of this term, as you can see. Now, squaring each term consists of what? You need to square the first part plus 2 times this one here times this one here, as we can see, plus the second part squared. Then we need to do this for the second term. We take the first part squared plus 2 first times the second plus the square of the second part, as we can see here. Then we need to regroup the terms in this equation. So what I did is I highlighted in blue the L2 squared. So I want to group these terms together. So I'll take this one, cosine theta 1 plus theta 2 squared, when I have it here, plus here we have sine theta 1 plus sine theta 1 plus theta 2 squared, and bring it here. Both of them are multiplied by L2 squared. Then I will do the same thing for the terms that have L1 squared in common. So I have this term here and I have this term here. So when you add them up together, I will have cosine 1 squared plus sine 1 squared, both of them multiplied by L1 squared. And the rest of the two terms, will I have this term and I have this term. Both of them, by the way, have L1 and L2 as a common factor. So one thing to note is that if you take the cosine square of a cosine of an angle plus square of its sine, this is going to give me 1 according to the last trigonometric identity here. So sine of an angle A squared plus sine of the angle cosine of the same angle squared, and the squared here is for the whole cosine, not for the angle itself. When they add them together, that's going to give you 1. So this can be replaced with 1, this can be replaced with 1, and it will reduce to L2 squared plus L1 squared plus 2 and we have the cosine of theta 1 plus theta 2 times cosine theta 1 plus sine theta 1 plus theta 2 times sine theta 1, all of these two terms multiplied by L1 and L2. Now looking at this one here, looking at the summation of these two terms, you can see that they relate to which identity matrix? Trigonometric identity. They relate to the second one, where I have a plus sign here. And have also a plus sign here. So cosine, cosine, sine, sine. So these can be replaced with cosine, the difference between the two angles. So we have A, in this case, going to be theta 1 plus theta 2. B, in this case, is going to be theta 1. So these two terms can be replaced with cosine of theta 1 plus theta 2 minus theta 1, which is basically cosine theta 2. Or we can write it as C2. So you can see how we started with a little bit long equation, but with a little bit of manipulation, it turned out to be much simpler than that. So have a good look at this equation, and you will realize that x squared is a known value because it's in the desired value for the position of the end effector for both x and y. So these are known values. L1 is known. It's a geometrical property of the length of the robotic arm. L2 is also known. So the only unknown here is a cosine of theta 2. So I would rewrite the equation such as theta 2 or cosine of theta 2 is on the left side of the equation. So everything else on the right side of the equation is known. So we know now cosine theta 2. What about finding sine theta 2? Finding sine theta 2, there is no way, if you look at these equations, equation 3 and 2, there is no way of really finding explicitly sine theta 2 from the equation themselves. So we would use one of the trigonometric identities where we talked about before, where the square of the cosine of an angle plus the square of the sine of the angle, they should give me 1, from which I would find that sine theta 2 is plus minus. It has two possible solutions here. Of under the square root, we will have 1 minus cosine theta 2 squared. So two solutions here. These represent two possible configurations or possible solutions for this robotic arm to achieve the same desired position for the end effector. Now, if you know, so here we found the value of cosine theta 2. So this is known value. So at this point we know sine theta 2. So this is known, so we can easily find the tan of the angle theta 2, and then the theta 2 itself is going to be inverse of the quantity here, which is sine theta 2 over cosine theta 2. And the inverse, or the instead of this case, in the inverse, we're going to use something called a tan 2. This is a MATLAB function that will give me the value of the theta, and not any value, but also with the correct quadrant. And we're going to talk about this in the next slide. So, but here, if I want to conclude, is we're going to say that this is an important relationship here, that it will give me the cosine theta 2. Using the trigonometric identity, I can find sine theta 2, and finally, with this relationship, I can find the angle itself, theta 2, both value and in which quadrant. So if you go into MATLAB and you say, for example, inquire about the function a tan. A tan is simply the inverse tangent, and this is going to give you a value, but not necessarily in the correct quadrant. So if you look here at the this is a plot of the tan function. You can see, for example, you can get a value for the tan equal to 1 at two different angles. It could be at an angle of 45 or also at an angle of 225. So they are about 180 degrees apart, or exactly 180 degrees apart. So which one is the correct angle? Is it 45 or is it 225? Now, in many other courses and many other applications, it wouldn't really matter a lot between 45 or 225. So it's not very sensitive really to in which quadrant the actual angle is. However, in robotics, it does really make a difference. And this is a physical angle. It's represent the rotation of the link. So 45 is of course different than 225. So we need to be able to determine exactly which one of them is the correct or the suitable answer for the case we have at hand. Now, so this is why in MATLAB we have another function which is a tan 2. The d here is for degrees if you want to have the answer in degrees. Otherwise, it will be in radians. So a tan 2d, this will give you the 4-quadrant inverse tangent. So it will give you both the angle and in the exact quadrant based on what? Based on y and x, where y and x are really the sine and cosine, because tan is basically sine over cosine. We will see an example with numbers later on and to see how does this really make sense or not. So we were able to find cosine theta 2, sine theta 2, and the angle itself using the a tan 2 function. Now, how about finding theta 1? Theta 1, we have to, for theta 1, we also need to look at the same equations. We'll still have equation 3 and equation 4. So from equation 3, we first of all, we want to try to expand this term, the cosine theta 1 plus theta 2. And to do that, we come to our trigonometric identities. So we have cosine of a summation of two angles. This can be easily written as cosine first angle, cosine the second, minus sine the first, sine of the second. So this becomes cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, all multiplied by L2, and this terms comes here. Then I'm gonna group terms together. I will have terms that have cosine 1 together. I have it in blue color here, and the rest of the terms, which is one term here that has S1, I will have it also alone by itself. So for the ones that have C1, I have cosine 2 L2 plus L1. So what we are doing, we are just rewriting the equation, equation 3. We are, moving around some terms. Now, cosine 2 is already found. L2 is a constant. L1 is a constant. So I can just give them a new name. Give this term a new name. Call it K1. And the same thing here. Sine 2 is given, already found before. L2 is also a constant. So I can call these as K2. So equation 3 can be written in a new way, that with x now being equal to K1, which is a constant, times cosine 1 minus K2 times sine theta 1. Good. So this is a new version of equation 3. We're going to do the same thing with equation 4. I want to expand the sine theta 1 plus theta 2, and this is by following the third trigonometric identity here. So we'll have sine of the first times cosine the second plus cosine the first times sine the second. So I'll have sine theta 1 times cosine theta 2 plus cosine theta 1 times sine theta 2. All of this is multiplied by L2 plus sine theta 1 L1. I'm gonna rearrange and group some terms together, the terms that contain S1, two terms here. So we'll have cosine L2 plus L1, have them all together here between parentheses, then multiplied by S1. And what's left here is S2 L2, and I have it multiplied by C1, which is cosine theta 1. Now, interestingly, this is the same term as the one we had here, which is K2. And here we have also this term is the same as K1. So we can rewrite equation 4 as y equals K2C1 plus K1S1. I'm going to move these two equations to the next slide. So this is the new form of equation 3, and this is the new form of equation 4. So I want to solve these two equations. These are non-algebraic equations, and we have to be a little bit innovative in solving these equations. So one way to do that is to rewrite them in like a polar type of coordinates. So instead of having the x and k1 and k2, I'm gonna have a length and an angle. So consider that k1 would be the length of one edge of a right triangle, k2, which is the adjacent, if here you want to call it. This is the opposite side of a triangle. This is k2, and we're going to do a transformation such as r, in this case, is going to be according to Pythagoras. It's going to be the square root of k1 squared plus k2 squared. So this is r. And in that case, the angle gamma is going to be tan k2 over k1. Or put in another way, gamma is going to be the a tan 2, which is the inverse of k2 over k1. So now, instead of using k1 and k2, we replace them with r and gamma. So k1 can be represented as r cosine gamma, and k2 is r sine gamma. So if you substitute k1 r cosine gamma into this equation, so instead of k1 I will have r cosine gamma, and instead of k2 I will have r sine gamma here, I'll get this equation. And do the same thing in this expression for y. Instead of k2 I have r sine gamma, and instead of k1 I'll have r cosine gamma. This also can be written here. So if I divide both equations by r, and I would need to notice that cosine gamma cosine theta 1 minus sine gamma sine theta 1 corresponds to the first trigonometric identity, where I have cosine cosine minus sine sine. So this is the cosine of a summation of two angles here being gamma and theta 1. And for the second equation also, we will have a sine cosine cosine sine, and we have a positive sign between them, a plus sign here. So correspond to the third trigonometric identity, sine cosine cosine sine, which is also sine of a summation of the two angles. And so it becomes sine of theta 1 plus gamma. If you divide this equation by this one here, so the r will cancel out with r, we'll have y over x, and we'll have sine over cosine, which is tan. And this is excellent because now we have reduced the original equation that had the theta hidden here. But now it will be easier to extract theta because I only have one function here, trigonometric function with this tan. Previously I had two functions. I have a cosine and a sine. It wasn't really easy to extract theta from it. So now I can easily extract theta because I can take the tan inverse. So if you take the theta 1 plus gamma will be the tan inverse or the a tan 2 function in MATLAB of y over x. Now you can take gamma to the right side of the equation, and again recall that gamma was defined as a tan 2 of k2 over k1. Now we no more need k1 and k2 because the whole idea of using them was to write things in a more compact way. That's it. So I replaced them back with the original formulas. So k1 was cosine 2L2 plus L1, and k2 was sine 2L2. So this is k2, this is k1, and now we have theta 1 on the left side. Everything on the right side now is known. Y is known, x is known, theta 2 is known. So yeah, that's it. We got theta 1 now. So given a certain desired position for the end effector, x and y, and we know the geometry of the robotic arm, we can calculate cosine theta 2. Then we substitute it into this relationship to calculate sine theta 2. It turns out that there are two possible solutions. We're going to talk about them in a second, from which we can really extract theta 2 here using this equation, and from which then we can calculate theta 1. So x and y will make me able to calculate cosine theta 2. Then if we substitute in this equation or this formula, we can find two values for sine theta 2. Each one of them will give me a certain theta 2 value, and each theta 2 value will give me a corresponding theta 1 value. So I'll get the solution for this problem will be a pair of theta 1 and theta 2. Two pairs, in fact. So so here in the figure we can see one possible solution, theta 1 value and the theta 2 value. The second solution would be a mirror image of what we have here. Let me try to draw this. So I will have here, let's say L1 should be a straight line anyhow as much as possible, and then I will have an L2 here. So this is L1 and this is L2. Let me change the color of it. So theta 1 in this case become this angle, and theta 2 you have to first of all extend L1, and theta 2 will be measured from here towards here. So this is the whole theta 2. So you can see that I have two solutions that will give me the same end effector position. Okay, so here we're gonna plug in some numbers in order to make sure that we understand the concepts. So for the same robotic arm, this time I'm gonna have a certain value for x and a certain value for y. X is the desired x is minus 1.1.12, and the y is 24.52 centimeters. And we are given that the length of link 1 is 25 centimeters and L2 is 20 centimeters. So directly we start substituting into the formula of cosine 2. So here we'll have for x we'll have minus 1.12, and for y we have 24.52. For L1 I have 25, for L2 I have 20, and I substitute the same thing for L1 and L2 here. So I will obtain a value for cosine theta 2 of minus 0.4225. Now this I can take it and plug it into the equation for sine theta 2. You see that you will get two values, one being positive 0.9 and the second will be negative 0.9. Now if you substitute the values for sine theta 2 and cosine theta 2. This is for cosine theta 2, this is for sine theta 2. Into this formula, I can get the a tan 2. So instead of sine theta 2 is 2, this is cosine theta 2, but I will have to consider both cases, the positive one and the negative one. So if I substitute this into MATLAB, as you can see here, this is the way you're gonna you have to submit the values into the a tan 2 function. So you will get an answer of 115 degrees. And if you do the substitute the other case, the other value for sine theta 2, I'll get the other option, which is theta 2 equal to 245. Now in MATLAB it gave me minus 115, but this is the same angle here, because if you add 360 to it, it's going to be 245. Both of them are going to be in the third quadrant. So this is going to be in the second quadrant, and this is in the third quadrant. So we have two possible values for theta 2. Okay, now I'm going to do an experiment here. So this is not to say that you have to do this, but this is an experiment just to see what other alternatives you'll have when trying to solve this a similar problem like this one. So now we're going to do the same as we did before. We're going to apply in the same formula. This is the value for cosine theta 2. Now, what if you wanted to use your calculator? So pick up a calculator, try to find the cosine inverse of a minus 0.4225. You are supposed to get 115, which is somehow it's the same as the first value we obtained before for theta 2. And now substitute the value for cosine theta 2 into the formula for sine theta 2. As before, we got a positive and negative 0.9. And now, using your calculator, calculate the inverse, sine inverse of the positive 0.9 and the negative 0.9. One will be giving you a 65, and one will be giving you a minus 65. So we're starting seeing some contradictory information. So what about if I do like substitute in the tangent formula? So theta 2. Now I want to find the a tan, not the a tan 2, just the a tan. This is the one that you'll get from your calculator. So if you take plus 0.9 for corresponding to the first possible solution over minus 0.4, this is going to give you from the calculator minus 65. If you're going to take the second solution where we have minus 0.9 over the minus 0.42, this is going to give me 65. So, however, when we use the MATLAB function, the a tan 2, it gave me 115 and it gave me 245. So, what's in the deal here? The deal here is that the a tan 2 is the correct one because it's determining in which quadrant the angle should be. And this cannot be obtained directly from the calculator because the calculator would give you just only one angle that correspond to a certain value for the tan, or for the sine in this case, or for the cosine. So suppose that you're in a case where you don't have MATLAB, you're in an exam or solving a quiz, and you wanna figure it out without really having MATLAB, and this is easy, in fact. So let's look at this case for theta 2 using just your calculator. So in the calculator you have plus 0.9 and minus 0.4. So you still you're gonna get minus 65, but now you have to identify that the plus 0.9 corresponds to the sine, and we know that the sine is gonna be positive in the first and in the second quadrants, whereas the minus 0.4, this corresponds to the cosine because tan is a sine over cosine. So this is the cosine here, and the cosine is negative in the second and in the third quadrant. So here all of them are positive. Sine is positive here, tan is positive here, and cosine is positive here. So the cosine is going to be negative either here or in here. So the quadrant that satisfies both conditions in this case is going to be the second quadrant here. So, but the angle that we got from the calculator is minus 65, and this is in the fourth quadrant. So to make it in the second quadrant, we have to add to it 180. So if you add 180, it's difficult writing using the mouse. If you add 180 to it, as you can see here, it's going to give me 115. And the same thing here. So let's see. I'm going to erase these. And here we have, I'm going to use the pen again. So we have minus, minus. So the sign is minus. The sign is negative in the third or fourth quadrants. And the cosine is negative in the second or third quadrant. So you can see that in here, in the third quadrant, both sine and cosine are satisfied. And however, 65 is in the first quadrant. So to find it in the fourth quadrant, I need to add to it 180, and this brings me to 245. So you can see that the correct answer is going to be 245 and 115. Then, so after determining theta 2, so once it's going to be, in one case it's going to be 115, in the second case it will be 245. So for the first case, you substitute it into the final relationship here, and y is known, x is known, and theta 2, we have it here. So you will find out that the theta 1, the corresponding theta 1 is going to be 45 degrees. And for this case, if you substitute 245 for theta 2, and you will find that the corresponding theta 1 will be 140 degrees. So then this is the solution for the example here. So we have two possible solutions to achieve an x position of minus 1.12 centimeters and then a y position for the end effector of 24.52 centimeters. If we use either the pair of theta 1 being 45 and theta 2 being 115, or alternatively if we used theta 1 equal to 140 and theta 2 equal to 245. Okay. Here we have another example where in this case we have a revolute prismatic robotic arm. Again, it's still a planar robotic arm with 2 degrees of freedom, but now we have one is a revolute, as we can see here, theta 1, and the second one is prismatic joint. So this link here can translate along this direction, whereas the first link can rotate about the z-axis here. So we are asked to perform the inverse kinematics for this robotic arm. We need to start with the forward kinematics. So for that we need to find the dh parameters. We have to take I from 1, 2, and 3 and find the corresponding dh parameters. We did this in the forward kinematics lecture for the same example also, and we were able to obtain these values. We substitute these values into the general transformation matrix for a link for frame I with respect to the one before it. So when you substitute in the values for theta, d, alpha, and a, you will be able to obtain or obtain the transformation matrices for the link 1, link 2, and also for the end effector. You can simply see here that for frame 1 with respect to frame 0, this is easy, and you can also obtain it directly by inspection, because we can see that frame 1 is rotated with respect to frame 2 about the z-axis. This is why we use the basic rotation matrix about the z-axis, and we see that they will have the same origin. Frame 2 with respect to frame 1, the orientation is a bit more complicated, because they have 2 rotations to reach from frame 1 to frame 2. And however, when it comes to the origin, frame 2 is translated with respect to frame 1 by a distance of d2 in the negative y1 direction here. And finally, between frame 3 and frame 2, they are both parallel. This is why we have the identity matrix here, and frame 3 is translated with respect to frame 2 by a distance of L2 along the Z2 direction. So to find the transformation matrix of frame 3 with respect to frame 0, I have to multiply these 3 matrices. And this is straightforward, and I will be able to obtain the final result here. This represents the forward kinematics that will be using it then for in the inverse kinematics analysis. So given any θ1 value and d2 value, I can obtain the final transformation matrix, which gives me the orientation and the position. So this is the final result. Just keep in mind that d2 here is variable, because the frame 2 with respect to frame 1 will be moving along this direction, as the whole link here would be moving, translating in this direction. And θ1 is also another variable. L1 and L2 are constants, and this is the result of the forward kinematics. So as we did before in the previous example, the inverse kinematics starts with comparing the result from the forward kinematics with the general transformation matrix for the end effector with respect to the base. Here we have the orientation of frame 3 with respect to frame 0. It's not intuitive, so we just keep it as constants here. And when it comes to the position of end effector with respect to the base frame, it's going to be at a certain desired x, y, and z. So if we compare this with the result of the forward kinematics, we'll have x is equal to this here, L2 plus D2 times sine θ1. Y is equal to minus L2 plus D2 times cosine θ1. Z is going to be equal to 0, because it's a planar robotic arm. There is no motion in the Z direction. So these are the two important equations that we obtained from this comparison. We will take these to the next slide. Now we're going to call this equation equation 1, this equation 2. So if we divide equation 1 by equation 2, we'll have x over y, L2 plus D2 sine θ1 over minus L2 plus D2 cosine θ1. This will cancel out with this. We'll still have the negative sign. Sine over cosine is going to be tan of θ1. From this expression, we can find the value for θ1, and it turns out to be the a tan 2, which is the tan inverse of minus x over y. We agreed before that a tan 2 is a MATLAB function that gives you the tan inverse and it gives you exactly in which quadrant it is going to be. So this is theta 1, and then going back to equation 1, we need to find the other joint variable, which is d2. So either you can go to equation 1 or equation 2, both would be okay. And so from equation 1, rearrange the terms in order to get d2 is equal to x minus L2 sine theta 1 over sine theta 1. And so because theta was already obtained, so this is known. L2 is a geometric property of the robotic arm. It's known. X is a desired value for the end coordinate for the end effector. So now D2 is done, is found, and this concludes the solution of the inverse kinematics problem. That's it for today.